Turing's proof of uncomputable numbers depended upon the proof that there is no algorithm that can determine whether or not a Turing machine will halt given some input. This problem, known as the halting problem, is logically equivalent to a result from the foundations of mathematics. In 1900, at the Second International Congress of Mathematicians, the esteemed mathematician David Hilbert presented a list of 23 unsolved problems in the field, representing critical challenges that face the foundations of mathematics. The second problem in the list concerned the consistency of axiomatic logic. Specifically, Hilbert sought for a proof that the axioms of mathematics and logic were consistent. In other words, could there be contradictions insidiously and unwittingly hidden within the axioms? A young Austrian named Kurt Gödel solved Hilbert's second problem indirectly. There are fascinating accounts of this work, but in brief, Gödel proved his now famous Incompleteness theorems, which state: 1. Any axiomatic system rich enough to model the natural numbers, for X-Maple, the Peano axioms, or the Zermelo-Frankel axioms, contains unprovable well-formed propositions. 2. Any axiomatic system rich enough to model the natural numbers can't prove its own consistency. At first, this was interpreted as a blow to mathematics because there was no way to prove that contradictions might not arise in logic and the proof of theorems. Moreover, there are an infinite number of unprovable theorems. These are true statements of the axiomatic system, but they are unprovable within that system. Gödel's theorems put an end to Leibniz's vision of a calculus ratiocinator that operated upon the characteristica universalis to mechanically and unequivocally validate any proposition. However, later researchers realized that these theorems implied that mathematics and logic could grow as far as creativity could take them. In essence, no algorithm could ever be able to mechanically crank out every possible theorem. Hilbert had also asked another question, the Entscheidungs problem, which asks a more modest question. Given a mathematical statement, can we prove if that statement is provable? Thus, instead of asking whether all of mathematics can prove itself consistent, can we even determine if a particular mathematical proposition has a proof or not? Observe that we're asking if the statement is provable, not what the proof actually is. In Turing's 1936 paper on computable numbers, referenced earlier, Turing proved the negative of the Entscheidungs problem. Namely, there is no algorithm that can determine if a given proposition has a proof or not. This feature of formal systems rich enough to model the natural numbers is known as undecidability.